Assalamu alaikum. How are you, my dear students? I hope you all will be in the best of health, wealth, and happiness. I welcome you all into my today lecture. Today is our lecture number 18, Unit 13, Electromagnetism. And today is the most significant part of the chapter. There is Ampere law, then the application of the Ampere's law, and then magnetic field due to current carrying solenoid, and the motion of the charged particle in magnetic field. So let us start with the name of Allah Almighty. Let us start with the Ampere law. Now, what is the Ampere law? The Ampere law is the most simple and powerful tool used to calculate the strength of the magnetic induction B around a current carrying conductor. This is the most easiest way. Just in the same way, if you remember the Gauss law, what was there in the Gauss law? In the Gauss law, what you studied there, that the Gauss law was what? That is the electric flux, if you remember, is equal to, that is the electric flux is uh, equal to the 1 over mu naught times the charge enclosed by that surface. And if you remember, at that point I told you that it is one of the powerful tools to calculate the electric field intensity due to any charge distribution in using simple mathematical tools, or in the simplest way. So if you remember there, I told you that if the charge distribution is known, then we can calculate the electric field intensity, right? In the same way here, this is an exactly matching to that, but that there was for the surface and it is for the line. There you are constructing a Gaussian surface. Here you will be constructing the Amperian loop. So what does this last states that? This last states that the product of what? The product of the product of the magnetic induction B, rather best to write that the dot product of the magnetic induction, the dot product of the magnetic induction, the dot product of the magnetic induction B and the length element, and the length element and the length element delta L is always is directly proportional directly proportional to the current enclosed, to the current enclosed by the circuit, to the current enclosed. Or in other words, we can also say that the that this last states that the dot product of what, or we can say that the dot product of the magnetic induction B in the length element delta L is equal to mu naught times the current enclosed by the circuit. So mathematically we can write that B dot L or delta L is equal to mu naught times the current enclosed by the circuit. Yeah, let me first write like this. It is directly proportional to mu naught times the current enclosed by the circuit, right? It is like this one. Or we can say that B, my God, I'm so sorry, class. What I'm doing, I don't know. That is that B dot delta L is directly proportional to the current enclosed by the circuit. Or B dot delta L equals mu naught times the current enclosed by the circuit. Now, what is this mu naught? This mu naught, it is what? The mu naught is the constant of proportionality, and this is known as the permeability. This is known as what? This is known as the permeability, permeability of the free space, of the free space. Experimentally, the value calculated for this mu naught is 4 pi into 10 raised to the power minus 7 Weber per ampere per meter. This is the value of this constant. Now, first of all, let me tell you about this constant, that what is the mean by the permeability. Permeability is, I would like to tell you that it is the strength of the medium around the current carrying conductor, the medium around the current carrying conductor. That could be a free space, that could be air or whatsoever, to exchange or to allow or to pass the magnetic field or the magnetic force. This is what I will tell you, right? And it is different for different media. In the same way, just like epsilon was the was there for the medium. So in exactly the same manner as your Coulomb force or electrostatic force depends on the medium, in the same way this shows magnetic force is also medium dependent, right? Now, this is exactly in the same pattern as that of your definition for the work done. If you remember, where you were looking for what? For F dot D. You see, that was your work done, and you see that the work was only done when the force and displacement was in the same direction. The same thing is exactly going to happen here, right? And I will now use this law for what? I will use this law for calculating what? For calculating the magnetic induction B around the current carrying conductor I, which is shown here. Now I just want to uh, uh, take your attention towards a very important point, and that is in your book. They actually told that, see here what they did. As I told you in the beginning, when I was explaining to you that the magnetic effect of the current carrying conductor, if you remember that, this tells you that B is directly proportional to I and B is inversely proportional to R, and then they simply tells you that this B uh, is directly proportional to I over R, and this B is what? It is equal to mu naught times into, then they tell you that 1 over R, and then they will tell you B dot R equals mu naught times I, and this is how the law is derived. So first of all, I just want to tell you that even if your book did this, I don't agree to the point, because laws are experimentally verified and they are investigated and discovered. In a way, a relation is discovered. It is not just like this that you will derive a law. So there is no point in it. But actually what they did it in the way for calculating what? The magnetic induction be at any point around a current carrying conductor. And you will see that when I apply this law, then you will exactly see how I do. For example, look, I will now, there is, your book mention only one application for this, and they use this thing as an application, sorry, as a law, but it is not a like a law. It is just what I will tell you, that that is what magnetic field, what magnetic induction. Yeah, magnetic field strength, magnetic induction or magnetic flux density B around what? At a point around a current carrying conductor, around a current carrying conductor. So I will use this law, the Ampere law, to calculate this. Now you see, look here, that let me clean this part. Let us see here. I just want to demonstrate this thing to you, and the law you already see. Now look, see here. If we have the, in order to apply the law, you need the current enclosed by the circuit. So you just look, see here, that this is what, if you connect this to the positive terminal of the battery, as you see, and this to the negative terminal of the battery, and definitely there will be a current flowing, and the direction of the current is shown, and then there will be a current I that is out of the plane or out of the paper. Now we want to calculate the electric field intensity B around a point. Now there is what, every point acts like what, it acts like a tiny magnet, right, with its direction indicated. This is north and this is south, as I just marked, north, south, like this, as you see. Now you look, as I told you, that every tiny point acts like a magnetic field. So to calculate this magnetic field around this, we construct what? First, we need to construct the Amperian loop. And what you see here, that look, this is what, this entire is actually what, for example, I started from this point X, as you see, and I arrive at the point X back. This is the Amperian loop which I constructed, right? Now I want to calculate the magnetic field strength due to this current carrying conductor at the point B, right, by using what? By using the Ampere law. Now you see that this is only possible, right, when the magnetic field B is along the length element. In the same way as I told you, that work is only done when force acts along displacement, or when the displacement is in the direction of the force. So the same thing happens here. Now let us see that we divide the entire length into the length element delta L1, starting right from here. Here it is delta L1, here it is delta L2, delta L3, delta L4, until you arrive to delta Ln minus 1 into delta L, right? And B is in the direction of what? B is in the direction of this, right, along the length element delta L. Now you just see, to apply what? To apply the Ampere law, look, we say that let there is what? I start from 1 up to n bi into dot delta Li into what? Into mu naught times I, that is the current enclosed by the circuit. Now look, whatsoever is the case, B1 equals B2 equals B3, it will be then equal to Bn will be equal to B. So B is constant. Why? Because around the current carrying conductor at the same R, there is, let me put this small R, at the same R or at the same radius, right? The magnitude of the magnetic induction B is the same at all point, right? Because it is at every point is at the same distance from the conductor along horizontal. So this is why I will just take this out, and what I'll be writing, is B into I start from 1 up to n into delta Li into mu naught times the current enclosed by the circuit. Now what I can write, see here, look, and that here it is going to be what? It is, let me just count for some, shift it, but move further. Sorry for taking time, but this disturbs. This is why I just want to create some space for me. And now what we can write here, that look, this B, and what I'll be writing, look, you have L1 plus L2 plus L3 up to Ln minus 1 and plus, sorry, delta L, delta L3, delta L minus 1 and delta Ln, right, into mu naught times the current enclosed by the circuit. And now what does this means? This means that, look, we have this thing B, and now what is this whole entire thing? Look, see here, if this is a radius and if this is delta L1, this is your delta L2, this entire, what does this make if you add all of them together? Nothing but the circumference of the circular path, circumference of the Amperian loop, Amperian loop, that is equal to what? Mu naught times the current enclosed by the circuit. This is what? This is that Amperian loop, as you see the circumference of the Amperian loop. So Amperian loop is what? It is in the shape of circular path, right? So what I will write here, you see this is B, and as this Amperian loop has radius R, so this is nothing but it is 2 pi R, right? And what I'll be writing, mu naught, right? And what is that current enclosed? The current enclosed is what? It is nothing but it is just this. There is only one conductor, no other conductor. So there is only the current, that single path current that is flowing through the conductor. So what I'll write, I. So let us see what happens. That this B equals what? Mu naught times I divide by what? Divide by mu naught times I divide by 2 pi R. Divide by what? Divide by 2 pi R. And this is what your book did, right? They did it what? Look, if you just see what happens, mu naught is constant, 2 pi is constant. So what does this means? That B is like this. So this is what the result which we can obtain from what? We can obtain from the Ampere law. Rather, deriving Ampere law from this relationship isn't good in this sense. Okay, so this is how he found the relation for this for the B and I. So you see that for the straight current carrying conductor, the magnetic field depends on the magnitude of the current, and it depends the radius, or it depends the distance of the point from the conductor, and the permeability of the medium around the current carrying conductor. So this is now a general equation which we will be using to calculate what the magnetic induction be around what, around any current carrying conductor. For example, you can use this equation to calculate the current carrying, to calculate the magnetic field around any current carrying wire, for example, in your home for the electric supply line, right? So this is how we can use the Ampere law to calculate the magnetic field induction. Now, the second important, right, as far as your exam is concerned, this is the another important point, and that will tell you that the finding what the that is second the second one is what, the second is the magnetic field. Yeah, the magnetic field the magnetic field due to due to a current carrying solenoid, due to a current due to a current carrying due to a current carrying solenoid, due to what, due to a current carrying solenoid. So you already learned in the class night that solenoid consists of coil more than one turn, or when a coil is wrapped around a cylindrical shape, then it forms a solenoid. And this is how you see here the solenoid. So we will just use make the use of this. So this is what, this is the, here it is what, here is the solenoid. Now we want to calculate the magnetic field be at the center of what, the magnetic field be at the center of, at the center of what, at the center of the solenoid. So now you see the lines are straight and parallel inside the center of the solenoid, so it means that the magnetic field is much more stronger there. Now look, and around here, this is the magnetic field is what, the magnetic field is very weak. Now let us see that, look here, we have this all L is the length of the, this is the length of the solenoid, and this length of the solenoid has turns per unit length, some turns per unit length, and we use a number called N, and that will be what, it will be the number of turns per unit length, or we can write N as N into L, right? So this is what, this is the number of turns, this small n is the number of turns per unit length in the solenoid. Here you see that this is connected with the positive terminal of the battery, this is connected with the negative terminal of the battery, EMF sources provide, and then there is the magnetic field. And now if you just see, look, the direction of the current here in this phase, this here at the back you see that the current is sinking, but here the current is rising. Okay, so at this point it is sinking, and at this point it is rising. So the sinking point where the current is into the paper, it will be marked as cross, and the rising point where the current is seem to be out of the paper or out of the plane of this laptop, that will be as circular dot. So cross here and dot here for every turn, right? Now let us see that, look, we want to calculate the magnetic field by using what, by using the Ampere law. Now what is the Ampere law? The Ampere law states that I starts from 1 up to n, B dot delta L equals what, it equals the uh, mu naught times into the current enclosed by the circuit. Now for this purpose, as I told you, that we must construct the Amperian loop first. This is very important to construct the Amperian loop. Now you see, look, that here we construct the Amperian loop in the form of what? In the form of rectangle, and you see here it starts from the point A, B, C, D, right? Now, and this portion only, for example, this could be extended to the length of what? To the length of the solenoid, like as you have seen here. Now, look, if you just see how many length element do I have? Here I have the length element delta L1, this delta L2, this delta L3, and this delta L4. This is the length element with me. Now let us see that look, you I starts from what? That is that I start from 1 up to 4 b dot delta Li bi into what? Into mu naught times the current enclosed by the circuit, right? Here I just label it as V1. Okay, here for example I will label it as B2, and here I will be labeled as B3 for example, and here I will be labeling it as, sorry, this is B3 and this is B4. Now this case is very much different from the previous one. Why? Because the magnetic field is not the same all around the current carrying conductor. B is stronger inside what? Inside the current carrying conductor, and here the B is what? The B is weaker. And here what? The B is what? Here the B is, and for this turn, look, is there any magnetic field? Do you see? No, there is no magnetic field line at this portion of the loop. So we consider it 0. For example, our B3 is equal to what? 0. That comes out to be what? 0. So how I can write that? I will be writing it B into delta L1 B dot what? Yeah, B1 dot delta L1. You can do it in number of ways. Plus B2 dot delta L2 plus B3 dot delta L3 and B4 dot delta L4 is equal mu naught times I enclosed. I means the current enclosed by the circuit. Now let us see this here, that what we can write that V1, since it is at the interior, and at the interior the magnetic field strength is B. Now you see that, look, what I will be writing here, B dot delta L1, right? And what here, that is B dot delta L1. So B delta L1 into cos of theta. Now look, the magnetic field, it is in this direction, and the length element delta L is also in the same direction. So what is the angle between them? Theta is 0. So cos of 0 I may write, right? So cos of 0 is equal to 1. So I will be writing what? Just B dot delta L1. For this, let us see that this does not contribute. There is no contribution from this term or from this expression. Why? Because if you just see, look, here this is the B2, and look for the length element delta L, and look for that very small value of the B here, which angle it makes with each other. Look, for example, they make an angle of what? This is B. If this is length element delta L2, this is theta is equal to what? 90 degree. And what is cos of 90? Since it is a dot product, so cos of 90 is 0. So the magnetic field strength is what? And the magnetic field strength is 0. So this does not, this end does not contribute, right? At what? It does not contribute, and this is 0. Similarly, that also does not contribute, and this expression is also set to 0. Why? Because it is not the angle here which matters. The angle does not matter here, but it is which thing which matter? It is this B, which is equal to what? 0, right? Because there is no magnetic field outside the Amperian loop which we have constructed, or that is very, very weak, and we consider it as 0. Similarly, this does not contribute because B and L are perpendicular to each other. So here B perpendicular to L, here B perpendicular to L. So this is why their contribution is 0, right? And the only contribution comes from this, right? So what I will write, that B into L delta L. So delta L is what? It is actually equal to the length of the conductor, right? L. So I'll be writing L. This entire I consider as delta L, this whole. Okay, so BL is equal to what? It is equal to mu naught times the current enclosed by the circuit. Now, what is the current enclosed by the circuit? Let me do this for you. Look, this current enclosed, I enclosed. Now, you have how many turns with you? You have that is the number of turns per unit length. You have what? You have this as, bulky, rather I will be writing it like this, that there are what? That there are n number of turns, right? And each turns continues what? And each turn carry a current what? I. So the current enclosed will be n into I. So what I will write here is n into I. But you know that what is this capital N? It is the number of that is, it is equal to the number of turns, this n number of turns per unit length. So this capital N is equal to N into L. So BL is equal to mu naught times N and L into I. And now you see this L and this L will get cancelled. And what is this B? It is equal mu naught times N into I. Mu naught times N into what? Mu naught times N into I. This is what? This is the magnetic induction B, which is equal to what? Which is equal to mu naught times Ni. Now, what does this mean? That B is directly proportional to the number of turns per unit length of the solenoid, and it is directly proportional to the current flowing. So there involve a geometric factors here. And what is that geometric factor? This N, right? Which is what? Which is the number of turns per unit length. So it depends on this geometric factor also. Now simply you can also write that that this equation can also tell that B is equal to what? Mu naught times the number of turns per unit length into L. In another way we can do this also. Okay, see here. And what does this mean? This means that B is directly proportional to N while keeping the length constant for constant length. For constant length. If you do not change the length and if you increase the number of turns, we get increase. And B is inversely proportional to the length, right? For constant N. For what? Constant N. So if you don't change the number of turns and you only increase the length, what happens? B becomes smaller. So this can be used to calculate the magnetic field and to calculate the magnetic induction for a solenoid, right? So this will calculate for UB. Our next topic is the force on current carrying conductor. Not force on current carrying conductor. That is the force on the charge particle, motion of the charge particle in magnetic field. Motion of what? The motion of the charge particle. Charge particle inside the magnetic field. Inside what? Inside the magnetic field. So whenever a charge particle enters inside the magnetic field, the charge particle experience a force, right? That is, the charged particle experience a magnetic force which is equal to Q into V cross B, right? That is the force which equals to what? Which is equal to V cross B. Now, what does this means? Are in the term of magnitude, this force equals Q into VB sine theta, right? It is equal to what? Q into VB sine theta. You see that, look, for example, if you have a charged particle, right? And if it is accelerated, and when this charged particle, for example, electron, when it enters into what? When it enters into the magnetic field perpendicularly, you see this is magnetic field, the cross B, it is into the paper. And this is the velocity of the electron as you see. Now, you already learned even in your class 9, when a particle moves, for example, in a horizontal direction, when a force acts from it from a vertical direction, it just compels the body to move around a circular track without changing in speed. So this is a kind of force which I call a deflecting force. Deflecting force. So whenever a charged particle enter into a magnetic field, it experiences what? A deflecting force which keep it move around a circular track around what? Around the which keep it what? Into a circular track inside the uniform magnetic field, right? As you see here, the strength of the force is directly proportional to the magnitude of the charge. It depends on the speed of the particle, and it depends on the magnetic field strength B. Greater the magnetic field strength B, the greater will be the force experience, right? Greater the velocity, greater force it will experience, right? The deflection force. Now, where does this force comes from? Because you know there is one permanent magnet. See here, this is what? This is permanent, a permanent magnetic field B, and one when, as you know, when the charge moves, right? When the charge moves, so there is what? There is magnetic field around this charged particle. So when the two magnetic field and interrupts together, they give rise to a kind of mechanical force that which we call the magnetic force, because it is the result of the two magnetic forces. And what happens? That acts in a direction perpendicular to the direction of the motion of the charged particle. And the charged particle tends to move around what? Around a circular path. Right now, there is the force will be maximum, right? This will experience a maximum force for sine theta equal 1 when the charged particle enters at right angle to the field. Means that when V perpendicular to B, then what will happen? It will experience the maximum force QVB, magnetic force, right, for that angle. And look, and the path will be what? It will be a completely circular path, right? Second, the as I told that the plane of the force is the direction of the force is perpendicular to the plane containing V and B. Now, another important point, when theta is what? When theta is in between 0 and 90 degree, right? When they are not perpendicular to each other, for example, look here, they are parallel. So when it is parallel, there are many cases. When look, when B parallel to V, right, then what will happen? This was case A. Okay, I'm so sorry, I'm in hurry because your timing is already finished and you will be waiting for your Zoom class. So this is case 1. V is perpendicular to what? B, and I told you the force will be what? You will see a maximum force, right? And then there will be a complete circular path, right? Maximum centripetal force. Case when V is parallel, so Fm will be equal to what? 0. What does this means? This means that the charged particle will experience what? Will experience no force, experience no force, no matter how large is the charge and how fast it moves, right? But when theta is 0, that is when it moves parallel to the magnetic field, then it will experience no deflecting force, right? And the case 3, when theta is less than 90 degree or equal and greater than 0, then what will happen? The path will be just, it is this case. See here, where is like this one, it is this case, right? So what will happen? That the path will be what? The path of the charged particle, it will travel along what? Along a spiral path, right? As you see. Clear? So this is how the image of the charged particle electron, right? When it is subjected to a perpendicular magnetic field, then the electron moves around what? Around a circular path inside the perpendicular magnetic field. Here, this is just another diagrammatical representation of this situation. Okay. So the clockwise or the counterclockwise depends whether the magnetic field is into the paper or out of the paper, or whether the charged particle is what? The charged particle is positive or negative. So the direction of deflection depends on this. So thank you very much for being here, and inshallah see you in the next class. And in the next class, I will explain this more elaborately, inshallah. So thank you for until now. Allah Hafiz.